There's a moment, usually late at night, where you catch yourself thinking about a decision you made years ago, a job you didn't take, a conversation you ended too soon, a door you walked past without opening. And you wonder, not with hope exactly, but with something closer to vertigo, what would have happened if you'd chosen differently? Most of us write that feeling off as nostalgia or regret. We chalk it up to human nature, this tendency to replay our choices like old film footage. But here's the thing that keeps physicists up at night, the thing that's quietly been building in the foundations of modern science for the last 70 years. That feeling might not be an illusion. It might be a glimpse of something real. Because according to some of the most serious, rigorous, peer-reviewed science being done today, there's a genuine possibility, not a metaphor, not a thought experiment dressed up as fact, but an actual, testable, theoretical possibility that the version of you who made the other choice exists somewhere, not in memory, not in imagination, somewhere. And if that's true, it changes everything, not just about physics, about what reality even is. This is the story of parallel universes, where the idea comes from, what it actually means, and why the deeper you go into it, the more unsettling it becomes. The first thing to understand is that parallel universes were not invented by science fiction. They were not cooked up in a writer's room to add drama to a storyline. They emerged almost reluctantly from the math. Science has a long history of arriving somewhere it didn't intend to go. Einstein didn't set out to discover that time moves slower near massive objects. He was trying to reconcile two existing theories that weren't quite agreeing with each other. The mathematics dragged him somewhere he hadn't planned to visit, and he followed, because when the math tells you something consistent and strange, you don't get to just ignore it. The same is true here. Multiple independent lines of physics, developed by different people in different decades, working on different problems, all seem to arrive at a similar suggestion. Our universe might not be alone. Now, before we get deep into the science, it's worth asking the obvious question. Why would any serious physicist entertain this? What's the motivation? Is it just that the idea is interesting? Because interesting alone doesn't get you into a journal. The answer is that in each of the major frameworks that predicts multiple universes, the multiverse isn't the goal of the theory. It's a consequence. Nobody set out to prove other universes exist. They were trying to explain something else entirely, the birth of our universe, the behavior of subatomic particles, the deep structure of space itself, and other universes kept showing up in the answer. Uninvited. That's what makes it worth taking seriously. It's not that physicists want it to be true. In some cases, they're almost annoyed that it keeps being true. So let's trace those lines. Let's go back to where they each start. To understand the first major argument for parallel universes, you have to go back to the very beginning. Not the beginning of time as philosophy, but the beginning as physics. The first fraction of the first second after the Big Bang. What we know from decades of observational astronomy and the precision measurements of the cosmic microwave background, essentially a faint afterglow of ancient light that fills the entire sky, is that the early universe was extraordinarily uniform. Too uniform, actually. regions of space that should never have been able to communicate with each other because they were too far apart for light to have crossed between them in the available time, somehow had nearly identical temperatures. This struck physicists as suspicious. Things don't match up by coincidence, not at this scale. In 1980, a young physicist named Alan Guth proposed a solution. He suggested that the very early universe went through a brief, violent period of exponential expansion, not the ordinary expansion the universe still undergoes today, but something almost incomprehensibly rapid. In a fraction of a second so small it doesn't even have an intuitive name, space stretched by a factor of at least 10 to the power of 26, possibly much more. Everything in the universe that we can observe today was originally a single, tiny, causally connected patch, and then inflation flung it outward, imprinting its uniformity across what became the observable cosmos. This theory, called cosmic inflation, did an extraordinary job of explaining the observations. The universe's flatness, its uniformity, the specific pattern of tiny fluctuations we detect in that ancient light inflation, explained all of it with a single elegant mechanism. But inflation has a problem. Or rather, it has a consequence that became its most provocative feature. Once inflation starts, it's hard to stop. According to the mathematics of inflationary cosmology, the process that drives inflation, a hypothetical energy field called the inflaton, doesn't switch off uniformly everywhere. It decays at random, quantum mechanical rates in different patches of space. Some regions stop inflating and become bubble universes, settling into relatively stable configurations like ours. But the space between them keeps inflating. It inflates faster than any bubble can eat into it, and so new bubbles form constantly, forever, in an ever-expanding sea of inflationary space-time. This is what cosmologists call eternal inflation, and it means that our universe, every galaxy, every star, every atom of everything we have ever seen or touched is just one bubble, one patch where inflation happened to end in a particular way. Out there, beyond any horizon we can observe or reach, other bubbles formed with their own properties, their own physical constants, their own versions of the laws of nature. Some of those universes might be nearly identical to ours. Others might have a different strength of gravity, a different speed of light, electrons with different masses. Most would probably be sterile. The conditions for stars, planets, and life as we know it are narrowly specific. But in an infinite space generating infinite bubbles, the math doesn't let you rule much out. This is the first road to the multiverse. It doesn't require exotic new physics. It's a near direct consequence of inflation, which itself is supported by strong observational evidence. Physicists didn't choose to arrive here. The theory brought them. The second road is older, stranger, and, in some ways, more disturbing. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions about the behavior of electrons, photons, and other subatomic particles have been confirmed to extraordinary accuracy, sometimes to more than 10 decimal places. There is no scientific theory that has been tested more thoroughly and agreed with reality more exactly. And yet, at its core, quantum mechanics contains something deeply weird, something that has never been resolved. When you observe a quantum system, say, an electron, you get a definite result. It's here or it's there. It has this spin or that spin. But before you look, the electron isn't in either state. It exists in what's called a superposition, a combination of multiple possible states, all simultaneously real, each with a certain probability of being observed. The moment you measure it, the superposition collapses to a single outcome. This is called wave function collapse, and it has been the source of philosophical headaches since the 1920s. The math of quantum mechanics describes the superposition beautifully, but the math doesn't tell you why, or even exactly when, the superposition becomes a definite thing. The collapse itself sits outside the equations. It's treated as a brute fact of measurement, not a physical process. In 1957, a Princeton graduate student named Hugh Everett III proposed something radical. He suggested that wave function collapse doesn't actually happen, that it's an illusion born of a limited perspective. His idea, called the many worlds interpretation, starts with a simple premise. Take the math of quantum mechanics completely seriously. Don't add collapse. Don't add a special rule for measurement. Just let the wave function evolve according to the equations, always and everywhere. What happens if you do that? If you run the equations without collapse, every quantum measurement results in a branching. When the electron spin is measured, and might be up or down, both outcomes occur. The universe splits into two branches, one in which the electron is observed as spin up, one in which it's observed as spin down. The observer in each branch sees a definite result. From inside any one branch, reality looks perfectly ordinary, perfectly single. But the full quantum state of the universe includes both. This happens constantly with every quantum event, every radioactive decay, every photon scattering off an electron, every chemical reaction in every cell of every living thing. The universe, according to Everett, is ceaselessly branching, generating an incomprehensibly vast structure of parallel histories, each as real as any other. The many worlds interpretation divides physicists. Some find it the most honest reading of the math, the interpretation that least requires adding unexplained elements to the theory. Others find it extravagant to the point of absurdity, a theory that multiplies realities without limit to avoid explaining collapse, which at least has the virtue of simplicity, but it has serious defenders. David Deutsch, one of the founders of quantum computing, considers it essentially the only coherent account of quantum mechanics. Sean Carroll at Caltech has written extensively and rigorously in its favor. The debate is genuine. The people on both sides are serious. What's striking is that, like eternal inflation, many worlds arrives at other universes not by design, but by following the logic of an existing framework wherever it leads. Whether or not you find it satisfying, it's hard to dismiss. There's a third, perhaps more intuitive route to other universes, and it has to do with the sheer size of the cosmos. When we talk about the observable universe, the sphere of space from which light has had enough time to reach us, we're talking about a region roughly 93 billion light-years in diameter. That sounds enormous, and of course it is, by any human measure. But here's the thing. There's no particular reason to think the universe ends at our observational horizon. Our cosmological models, and particularly inflation, strongly suggest that space extends far beyond what we can see, possibly infinitely. If space is infinite, then it contains an infinite amount of matter arranged in an infinite variety of configurations. And in an infinite set of configurations, every possible arrangement of particles will occur not just once, but infinitely many times, including, somewhere, an arrangement identical to the one that constitutes you. This is a sobering thought, and a strange one. It isn't about quantum branching or bubble universes. It's just arithmetic and geometry. If the space is truly infinite and matter is distributed within it according to the same physical laws we observe here, then the universe contains exact copies of our planet, our solar system, our galaxy separated from us by distances so staggering they make the observable universe look like a mote of dust. Cosmologist Max Tegmark has calculated that the nearest such copy, an exact duplicate of the Hubble volume, the full bubble of space that surrounds us, would be roughly 10 to the power of 10 to the power of 118 meters away. A number so large it doesn't correspond to anything in human experience. But in an infinite universe, it exists. This isn't mysticism. It's combinatorics applied to cosmology. If space goes on forever, and particles can only arrange themselves in a finite number of distinguishable ways within a given volume, eventually every arrangement recurs. The fourth road is the most speculative and, perhaps, the most intellectually ambitious. String theory began in the late 1960s as an attempt to describe the fundamental constituents of matter, not as point particles, but as tiny vibrating loops or strands of energy. Over subsequent decades, it evolved into the leading candidate for a unified theory of physics, a single framework that could reconcile quantum mechanics with general relativity, two theories that are individually extraordinary but mathematically incompatible with each other. String theory requires more dimensions of space than we observe, typically 10 or 11 total. The 6 or 7 extra dimensions are thought to be curled up, compactified, at scales so small they're invisible to any probe we've built. But they don't go away, and the specific shape in which these extra dimensions curl up their topology determines the physical laws of the universe in those dimensions. Here's the alarming part. The number of distinct ways those extra dimensions can curl up is staggering. Estimates range from 10 to the power of 500 to much larger numbers. Each configuration is a valid solution to the equations of string theory. Each gives rise to a universe with its own set of physical constants, its own strength of gravity, its own value for the cosmological constant, its own mass for the electron. Each is a distinct universe in what string theorists call the landscape. The landscape dovetails with eternal inflation in a way that some physicists find almost too convenient. If eternal inflation is constantly generating new bubble universes, and if the physical laws of each bubble are determined by a random selection from the string landscape, then the full picture is a vast multiverse in which virtually every possible combination of physical laws is realized somewhere. Our universe would be one of those bubbles, the one that happened, by chance, to have the precise combination of constants that permits stars to form and chemistry to happen and life to arise. This has enormous implications for one of the oldest puzzles in physics: why our constants have the values they do. Why is gravity so precisely the right strength? Why is the cosmological constant so astonishingly close to zero? In a single universe, these fine-tuned values demand an explanation. In a multiverse with 10 to the 500 variations, they require no explanation at all. We find ourselves in a universe compatible with our existence simply because we couldn't find ourselves in any other kind. This is what physicists call the anthropic principle, and it's either the most elegant idea in cosmology or a profound abdication of explanatory responsibility, depending on who you ask. Let's slow down for a moment and really sit with what any of this would mean if true, not the equations, the implications. Oh, if the many worlds interpretation is correct, then every decision you've ever made, every fork in the road, spawned a new branch of reality. The job you took and the one you didn't take both exist. The person you ended up with and the person you walked away from both continue in worlds that diverged from yours at some definite moment. Your life is not a single path. It's a tree, endlessly branching, with every version of you equally real, each unaware of the others. If eternal inflation is correct, there are universes out there physically identical to ours, right down to the layout of your childhood bedroom, the exact words of an argument you had at 19, the particular slant of light through a window on a Tuesday afternoon. Not similar, identical. And then a version where one photon scattered slightly differently, and another where a gene expressed itself differently, and on, diverging in every direction. If the string landscape is correct, there are universes where the force of gravity is strong enough that gas clouds collapse before they can form stars, and life of any kind is impossible. Others where atoms can't form at all. A vast, dark parameter space of uninhabitable configurations, and in the tiny, habitable corners, islands of chemistry and light. These ideas are not easy to accept, and they shouldn't be. The human mind evolved to track a single timeline, one world, one set of consequences, following from one set of causes. The multiverse asks us to hold something our intuitions actively resist: the idea that every path is taken simultaneously, that our sense of singular reality is local, not universal. Philosophically, the multiverse raises questions that physics alone cannot answer. If every possible history occurs, what does it mean to make a choice? If you are going to branch, in some sense, no matter what, with one version making one decision and another making the opposite, is anything actually decided? Or does free will become a kind of local experience, real within a single branch, but meaningless across the whole structure? These aren't idle questions. They matter to how we understand moral responsibility, identity, and the significance of individual lives. A version of you who never makes a mistake exists somewhere in the many-world structure. So does one who makes nothing but mistakes. Both are you, in some meaningful sense, and yet they couldn't be more different. In what sense, then, is you a coherent concept? Something happens to people when they genuinely internalize the multiverse. It's not the same as learning about the Big Bang. or the age of the stars. Those facts are staggering, but they're about scale, and the human brain, while unable to truly picture a billion light-years, can at least place itself conceptually within a larger story. You're small, but you're here, in the middle of it, and the universe's history leads to you. The multiverse doesn't do that. It removes you from the center of even your own story, because if every outcome occurs, you are not the protagonist of a narrative with meaningful stakes. You're one thread in an incomprehensible tapestry, and the tapestry is being woven in every direction at once. Some people find this liberating. The physicist David Deutsch has argued that the existence of parallel worlds makes your choices more significant, not less, because it means you are constantly participating in a branching structure where what you choose determines which kind of being you are, even if all choices occur somewhere. The universe in which you acted with courage is real. So is the one where you didn't. The difference between those is you. But plenty of people find the opposite. A kind of quiet vertigo sets in. If the me who finished the project and the me who abandoned it both exist equally real, then what does finishing it mean? The success isn't unique to me, it's just the branch I happen to inhabit. The failure is also real, in a sense, just over there. There's also a peculiar kind of grief that the multiverse makes possible. In the many worlds picture, every person who has died still exists in the branches where they didn't die, where the accident didn't happen, where the diagnosis came back different, where they turned left instead of right. This isn't comfort, exactly. You can't reach those branches. You never will. But they're there, and in some sense, those people are still alive. That thought can feel like relief, or like a particularly cruel trick of the mind, depending on the moment and the loss. The multiverse also has something to say about regret. Every deeply human wish, if only I had done this differently, might correspond to an actual world where you did. The version of you that didn't make the mistake exists. It just isn't you, the reader of this sentence, the person watching this screen. Whether that's comforting or hollow is a question only you can answer. What's notable is that these are not frivolous psychological reactions. They're tracking something real, that the multiverse, if true, fundamentally restructures the relationship between choice, identity, and meaning. It doesn't destroy those concepts, but it bends them in ways our intuitions were never built to handle. Here's the critical test. Science isn't just about generating elegant ideas, it's about testing them. And the multiverse presents one of the hardest problems in the history of empirical science. How do you find evidence for something that, by most definitions, lies beyond what we can ever observe? This is where the debate gets sharp, even among physicists who believe the multiverse is real. Karl Popper's standard for science, that a theory must make predictions that can, in principle, be falsified, is genuinely difficult to apply here. If other universes are causally disconnected from ours, separated by distances no signal can cross, or living in separate branches of the quantum wave function that never interact, then how do we detect them? The answer depends heavily on which kind of multiverse you're talking about. For the bubble universes of eternal inflation, there's one tantalizing possibility. During the inflationary period, bubble universes expanded and were pushed apart. But some models suggest that early in their histories, two bubbles could have collided before they separated beyond contact. A bubble collision would have left a specific imprint in the cosmic microwave background, a subtle circular pattern in the temperature fluctuations of that ancient light that fills the sky. Astronomers have looked. The Planck satellite, which mapped the CMB with extraordinary precision, has been searched for exactly this kind of signature. So far, nothing definitive has been found. But the search isn't over, and next-generation observatories are being designed with sensitivity that might push the limits further. A genuine detection would be one of the most extraordinary events in the history of science. Its absence, however, doesn't rule out bubble universes. It just means either no collision happened in our past, or the imprint was washed out by subsequent physics. For the many worlds interpretation, detection is even harder to conceptualize. In principle, branches in the wave function don't influence each other once they've sufficiently decohered the process by which quantum superpositions lose their quantum character through interactions with their environment. Decoherence happens fast, effectively instantaneously on human scales. The two branches containing different outcomes of a coin flip diverge so completely and so quickly that they become, for all practical purposes, causally independent. But for all practical purposes isn't forever. The Everetian structure of quantum mechanics is technically reversible. Under an extreme and perfectly controlled experimental environment, impossibly perfect, far beyond anything currently conceivable, a decohered branch could, in principle, be recombined with its twin. This is essentially what quantum interference experiments already demonstrate at the microscopic level. You can show that a particle took two paths at once by allowing those paths to interfere with each other. Some physicists argue that, in principle, sufficiently powerful quantum computers might demonstrate something analogous for larger systems. David Deutsch believes that quantum computation itself is evidence of parallel universes because the quantum speedup arises from calculations running simultaneously across multiple branches. This is a minority view and a contested one, but the broader point stands. In the quantum world, interference patterns already hint at a structure beneath our single-branch experience. For the string landscape, any empirical handle is even more remote. The landscape predicts that the cosmological constant, the mysterious energy of empty space that drives the universe's accelerating expansion, should be drawn from a vast range of possible values. The specific value we measure is extraordinary, absurdly small from a theoretical standpoint, but precisely within the range that permits structure and life to exist. The multiverse provides an anthropic explanation for this, but anthropic arguments are not predictions in the normal scientific sense. They don't tell you what to look for. They tell you, after the fact, why the value you found is the one you'd find. Some physicists, including Nobel laureate Steven Weinberg, have argued that the anthropic reasoning in the context of the string landscape actually constitutes a real prediction. Before the cosmological constant was directly measured, the landscape argument suggested it would be small but non-zero. When it was observed to be exactly that, some regarded it as a genuine success for multiverse reasoning. Others were unconvinced. That debate continues. The honest summary is this: we do not currently have direct observational evidence for any form of parallel universe. We have theoretical frameworks that require or strongly suggest them. We have experimental hints at the quantum level that are consistent with branching wave functions. We have anomalies in the cosmic background radiation that are being investigated, but confirmation, the kind of evidence that would settle the question, doesn't yet exist and may never exist. This doesn't make the idea wrong, it makes it hard, and that's a different problem. Let's talk about the parts nobody's quite comfortable with. The multiverse, at its most extreme, has a feature that is genuinely troubling to many physicists, not just philosophically, but scientifically. It may explain too much. If the string landscape contains 10 to the power of 500 distinct universes, each with different physical laws, then virtually any observation you might make is compatible with the theory. The cosmological constant is small. That's in the landscape. Suppose it were large. That would be in the landscape too. The mass of the proton is what it is. Sure. Different. Also there. A theory that can accommodate any possible observation is a theory that predicts nothing, and a theory that predicts nothing, in the Popperian sense, isn't science. This is the anything goes problem, and it haunts multiverse cosmology. Critics like Paul Steinhardt, one of the original architects of inflation, have argued that if eternal inflation produces every possible kind of universe, then it explains nothing about our particular universe. Why do we have the constants we have, the particle masses we observe, the cosmological constant we measure? The answer, under the full multiverse framework, is because we're in the branch where those values permit observers, which is true and also useless as a scientific explanation. Lee Smolin, the physicist and writer, has gone further, arguing that a physical theory's primary job is to make testable predictions about the world we inhabit, and that a theory which can only be vindicated by appeal to an unobservable ensemble fails that test entirely. He's proposed alternative frameworks, notably his cosmological natural selection idea, where universes reproduce through black holes and undergo a selection process that favors life-permitting physics as a way of making the problem tractable again without giving up on prediction. There's also something existentially uncomfortable about determinism in the many worlds picture that deserves more attention than it usually gets. If the wave function of the universe evolves deterministically, and it does, according to the Schrödinger equation that governs quantum evolution, then every branch that exists was always going to exist. The branching isn't random in any deep sense. It's mechanical. The structure of the full quantum multiverse is fixed by the initial state of the universe and the laws of physics, which means, in the strongest reading of many worlds, not only does every outcome occur, but it was determined from the beginning that every outcome would occur. Free will, in any strong sense, doesn't get more room to breathe here, it gets less. And then there's the identity problem. In the quantum picture, every decision creates two versions of you, both continuous with the person you were a moment before. But after the branch, each version has a separate future. Each will accumulate different memories, different relationships, different selves. After enough divergence, are they the same person? If you split this very moment, one branch in which you continue watching, another in which you stop, is the person in the second branch the person who chose to stop? Or is the choice not a choice at all, because both branches were always going to happen? These questions can't be answered by physics alone, and perhaps that's the deepest discomfort the multiverse creates. It takes questions that have always seemed like the territory of philosophy and religion, questions about the nature of the self, the meaning of choice, the significance of individual experience, and suddenly drags them into the domain of empirical physics, without providing any tools to answer them. Despite all the challenges, the field isn't standing still. One of the most active areas of current research involves trying to identify what, if anything, could distinguish between the different types of multiverse, or between a multiverse and no multiverse at all. This is harder than it sounds, but not impossible, and it's where the next generation of theoretical and observational tools will be focused. On the observational side, upcoming CMB experiments, including the Simons Observatory, currently under construction in the Atacama Desert in Chile, and the proposed CMB S4 project, a network of telescopes that would push sensitivity several orders of magnitude beyond Planck, will map the ancient light of the cosmos with unprecedented precision. If bubble collisions left any imprint at all, these instruments have a real chance of finding it. If they find nothing, that genuinely constrains the models. There's also growing interest in the gravitational wave sky. The LIGO-Virgo network has already opened a new observational window on the universe, detecting the ripples in space-time caused by colliding black holes and neutron stars. As these detectors grow more sensitive, and as next-generation space-based detectors like LISA come online in the 2030s, it may become possible to probe aspects of the early universe that are invisible to light, including signatures of phase transitions in the early cosmos that certain multiverse models predict. On the theoretical side, the challenge is to make multiverse frameworks more predictive, not less. This is the core critique, and it's driving serious research. Some theorists are working on what they call measure theory in eternal inflation, essentially a way of calculating the probability of finding yourself in one kind of universe versus another, given the vast and varied ensemble. Without a well-defined measure, the landscape's anthropic explanations collapse into circular reasoning. With one, there's at least a principled basis for prediction. In quantum foundations, the experimental program around quantum decoherence and interference is advancing rapidly. Quantum computers are becoming capable of demonstrating coherence and interference over larger and larger systems. While they're still far from the scales at which we'd hope to see genuinely macroscopic branching, each step forward in quantum control is a step toward the kind of experiment that might, in principle, provide indirect evidence for the many-world structure. There's also an emerging connection between the multiverse and theories of quantum gravity, the still incomplete theory that would unite quantum mechanics and general relativity. The holographic principle, which emerged from string theory in the late 1990s through work by Juan Maldacena and others, suggests that the information content of a region of space can be encoded on its boundary, like a three-dimensional image stored on a two-dimensional surface. Some researchers believe this duality has deep implications for the structure of space-time and the nature of parallel universes, that the many branches of quantum mechanics and the many bubbles of inflationary cosmology might ultimately be aspects of a single, deeper quantum gravitational structure. This is highly speculative. But it's productive speculation, the kind that generates new mathematical tools, new ways of thinking about old problems, and occasionally, the kind of unexpected connection that changes everything. The broader trajectory of physics suggests that the next 50 years will be transformative. The James Webb Space Telescope is already delivering data about the earliest galaxies in a way that tests cosmological models in new regimes. Particle physics, while facing a genuine crisis of expectation after the Higgs discovery, wasn't accompanied by the supersymmetric particles many theorists anticipated, is pushing toward new collider proposals that might probe energy scales never before reached. And the theory of quantum gravity, which has been tantalizing and elusive for nearly a century, might finally be cracked not through a single dramatic breakthrough, but through the quiet accumulation of consistency across different theoretical frameworks. If and when we arrive at a complete theory of quantum gravity, it will almost certainly have something fundamental to say about the structure of space-time at its most basic level, about what it means for something to exist, about whether other spaces, other histories, other laws of physics are real features of the fundamental theory or mere mathematical shadows. That will be a moment of genuine reckoning for physics and for how we understand ourselves within the cosmos. Here's what we actually know at the end of all of this. We know that the universe is staggeringly large, so large that significant portions of it are permanently beyond our observational reach, not because our instruments are insufficient, but because the universe is expanding and light from those regions will never reach us. We are already and irreversibly isolated from most of what exists. We know that quantum mechanics, the theory that governs every atom and every interaction in the physical world, describes a reality in which superpositions of multiple states are the rule, not the exception, and that the mechanism by which those superpositions become the definite reality we experience is, depending on your interpretation, either a brute fact of nature or the branching of the universe into parallel histories. We know that the theory of cosmic inflation, supported by multiple independent lines of evidence, strongly suggests that the universe extends far beyond what we can see, and that the same physics which explains our observable cosmos naturally generates an eternal, self-reproducing process that gives rise to what may be an infinite number of distinct regions of space. And we know that string theory, our most developed candidate for a complete unified theory of nature, contains a landscape of possible physical laws so vast that it cannot be explored even in principle, and that somewhere in that landscape may lie the reason our universe looks the way it does. What we don't know is whether any of this is true. Not in the dismissive sense, of course, these ideas might be wrong. Most ideas are wrong, but in the deeper sense, we don't know whether the kind of knowledge we're seeking here is even the kind of knowledge physics is built to provide. We've spent 300 years building a machine for predicting outcomes of experiments we can perform in the world we can access. The multiverse asks whether that machine can say anything meaningful about what might lie beyond access. Some physicists believe it can. They argue that mathematical consistency, predictive power within the observable sector, and the elegance of a unified framework constitute genuine evidence, even in the absence of direct observation. Others believe this is where physics ends and metaphysics begins, and that confusing the two is how science loses its grounding. Both positions are held by serious, brilliant people who have devoted their lives to understanding the universe. The disagreement is real, and it isn't close to being resolved. But here's what strikes me, sitting with all of this. The very fact that we're asking the question, that our species has developed the mathematical tools to even formulate the multiverse as a possibility, is itself extraordinary. We are a temporary arrangement of atoms on a pale blue rock, circling a middle-aged star on the edge of a fairly ordinary galaxy, in a cosmos whose total extent and nature we can barely even guess at. And yet somehow we've developed methods of reasoning precise enough to follow the logic of our own existence back to the moment of creation, and forward to the possibility that our universe is one among an uncountable multitude. That's not nothing. That might, depending on how you hold it, be everything. The question of parallel universes may not be answerable in our lifetime. It may not be answerable at all, with instruments made of matter operating within the single branch of reality we inhabit. But the question itself is a kind of mirror. It reflects back to us the limits of human knowledge, the audacity of human curiosity, and the strange, humbling fact that a universe capable of giving rise to questions like this one might already be its own most remarkable feature. Somewhere, maybe, another version of you is finishing this sentence too. Same words, same thought, looking out at the same idea from the same cognitive angle, wondering the same thing. Or maybe not. Maybe there's only this screen, this moment, this single unwavering thread of experience running through a cosmos that is finite and whole and entirely without parallel. We don't know, and somehow that's the most thrilling thing about it.